obviously now it's looking blurry because you're not getting the two pictures independently, one into each eye. People learned to keep their heads kind of steady. It wasn't that big of a problem. But now, if you go into one of the latest 3D movies and you have your polarizing sunglasses on, I'm sorry to report you can't make the screen turn black by going like this, because they've moved on even more. They've moved into what's called circularly polarized light. So instead of just coming at you vertically or horizontally, what they do is that the polarization plane rotates. One's like this, and one rotates like this. So it's basically one corkscrew like this, and one corkscrew like this. So basically the transmission axis for those things carves like a corkscrew through there, like this. One is clockwise, one is counterclockwise. So only a light that can exactly track that transmission axis as it passes through the lens can get through there. So the advantage, of course, of that is that if you have one of the corkscrews transmission axis winding like this and the other one like this, they're never going to be able to mix. And because it's a circle, you're never going to get mixing, right? I don't know if that makes any sense. But nowadays, you can go like this during a 3D movie and everything's fine. Question?
Is it all in the projection, so it doesn't matter how you film it, except that you want to film it at the...
That's exactly right. So you want to film it in such a way that you have two images that are this is assuming it's live action. If it's on a computer, you can just sit there and do it, right? But if it's live action, they're filming it two different cameras that are slightly apart. And then when they decide to project it, they have to just have a special projection system, including the screen, so that it can get back to your eyes, bounce off the screen to your eyes as polarized light. Okay, so that's just a little bit about, that's a very nuts and boltsy example. Let me talk about how this enters into the real world. Obviously, everything I've been talking about so far is relying on specially manufactured equipment. You can polarize stuff just fine in the natural world. So let me talk about the law of reflection. When light reflects, so let's say you have some kind of surface that light is bouncing off of. So let's draw in the direction of the light. Let's say the light comes in from like that direction. That's called, by the way, a light ray. A light ray is just an arrow indicating the direction of travel. It doesn't have any other properties. And the agreed upon method for talking about how it comes in and interacts with the surface is to drop a normal line to the surface. So if we want to talk about what angle does this light hit the surface with, we would actually talk about this angle right here. We call this the incident angle. Okay? So I stands for incident, or if it helps you, you can think of it as standing for incoming. It doesn't really matter. But that's the agreed upon way to measure that from the normal to the surface. The law of reflection is the most boring law ever. It says that the reflected angle is equal to the incident angle. So it bounces off at the same exact angle to the normal, like so. Why is it like that? Well, a lot of this stuff I'm not going to get into really. It turns out if it wasn't like that, you'd be violating energy conservation. So let's make sure that the angles are equal. So we'll do a lot more stuff with reflection as we go forward. But for right now, I do want to point out something, is that if the light is unpolarized coming in, so if this is unpolarized light, we will find that this property is not necessarily preserved on the bounced or reflected light. And I'll tell you why. The unpolarized light, of course, represents that the electric field is wiggling in all directions. So as it comes down to interact with the surface, some of it's wiggling like this, right? Some of it's wiggling like this. And where the reflected beam comes from is that the light comes down, it interacts, these electromagnetic waves will interact with the charges in the atoms of the surface. It'll make those charges shake, and then that is the source of the reflected light. Okay? So that is how the light can change paths. It's actually new light being created by the oscillation of charge in the surface. So if you were to zoom into the surface here, what you would see, just to greatly exaggerate, you would see, of course, a bunch of charges and atoms. I don't know why I just drew the positive charges. But those charges get picked up, right? Electromagnetic wave comes and affects these charges. Really, the electromagnetic wave is just the electric and magnetic field. It just happens to be oscillating with time. So charges from far away are interacting with these charges. And the way they're doing it is an electromagnetic wave. Well, there's a direction that these guys can oscillate easier or harder. It's actually a lot easier to oscillate in the plane of the thing than to oscillate off the plane. So you can imagine that it's a lot easier to just kind of jostle around next to your, back and forth next to your neighbors than to completely jump off the plane of the material, right? And so that means that what gets made in the reflected light is not equal. What you will find, because it's a lot easier for charges to oscillate in the plane or that in the plane of the material, you will find that the polarization that is parallel to the surface is far more represented. It's not that the other stuff isn't there, but the more it has to be made by charges oscillating off the surface, the less prevalent it is going to be. Okay? So what you will find is that the reflected light is highly polarized parallel to the reflecting surface. Anytime light bounces off of something, it becomes highly polarized parallel to the surface it just bounced off of. And in this case, since of course we have a horizontal surface, then we will have highly horizontally polarized light. Now, it's not that the other polarizations aren't there, they're just far more, or far less represented, okay? Now, in the interest of full disclosure, telling you a topic that I'm not going to get a chance to get into, there is one incident angle where it's not just highly polarized, it's perfectly polarized. So there is a special incident angle. It's called Brewster's angle. In case this ever comes up in your life somehow, I can't imagine how it will, but there's a special incident angle where it's perfect polarization. So it's not just highly polarized parallel to the reflecting surface, it is entirely polarized. Now, the reason I don't get into that is that the chances of exactly hitting Brewster's angle by accident is pretty slim. But for a wide range of angles around it, you will find that this condition is almost met. And so it's more important for me conceptually that you understand that for a large range of incoming angles or incident angles, the light that might be unpolarized on its way in will be highly polarized parallel to the reflecting surface on the way out. So we can now design some sunglasses. Let's make some sunglasses. Your sunglasses should have their transmission axes, if they're polarized sunglasses, with vertical transmission axes. Why vertical? Well, it's because most of the light that is bouncing off and getting in your eye, which we call glare, is horizontally polarized light because it's bouncing off horizontal surfaces, like the road, like a lake, or the ocean, the hood of your car. These are all things where even if you're not staring into the sun and getting direct sunlight, you're getting reflected sunlight, which can be disturbing, right? So one of the things you can try if you own a nice pair of polarizing sunglasses, it works better at some times of day than others because the closer you are to Brewster's angle, the better it is. But you can literally go like this and see the brightness of the road change when you're driving around. Okay? sometimes do this to try not to get in an accident. But you can see that there's a significant change in brightness. You will find that when you tilt your head like this, and the transmission axes, of course, are now horizontal, they will let in much more light because the light that's coming at you is more horizontally polarized. Okay? So you may notice this if you're lying on the beach and you're lying on your side. You may notice that the sun is brighter than it was when you were standing vertically, and that's because, of course, you've rotated your transmission axis. Okay? So this gives us a roadmap. If the sunglasses that you're supposed to be wearing have vertical transmission axes, then it gives an opportunity to make sure that heads-up displays work, or any kind of LED is coordinated with this. For instance, a wristwatch that has an LED display, you want the light coming off of it that isn't black already. You want the white part, you want it to have vertically polarized light because that's going to get in through your transmission axis. You can actually take one of these wristwatches that you're supposed to look at like this, go like this, and make it turn black. You can try it if you have polarizing sunglasses. So it's designed to be looked at like this. It'll go black like this. Computer screens also, the light coming off computer screens is polarized. If you're ever working on the computer with sunglasses on, try going like this. You can make the screen turn black at the right angle. Okay? And of course, they also try to make sure that when you're at the gas pump or you are your LED display on your car, they try to make it have vertically polarized light so that the hope is that you can, of course, see it when your head is in the orientation it's supposed to be. You can always mess with it by going like that. Okay? So that's how polarization comes up in real life. Light can highly polarize by reflection. It should be noted that human beings can't observe polarization states with the naked eye, but many, many different creatures can. Some insects navigate by polarization. So different parts of the sky have different polarizations because, of course, the way that you see any part of the sky that's not directly the sun is by blue sky is from sunlight bouncing off those atmospheric particles. And then the angle at which they bounce off will determine their state of polarization. Okay? So there's a lot of interesting stuff where we not able to partake in this phenomenon with the naked eye, don't see a lot of what's going on in the world around us. Just to give you another example, here is a piece of polycarbonate, basically fancy plexiglass, and you don't notice anything unusual about it. When I tighten this up, I'm of course stressing these the joints here a little more. You can't see anything, but if we open ourselves up to the hidden world of polarization, so first of all, you can notice that even though I have these two transmission axes crossways, there are spots there where the light is getting through, right? So clearly, the crystal structure of this thing is affecting the polarization of the light. You can also see it's color dependent. So it turns out that you can not only polarize things, but you can pick out which colors you're polarizing in what way. And the point I want to make here is that if I stress this, you should see the colors evolve. You basically have a visual representation of how I'm stressing the crystal structure of this thing. Okay? There's a lot of stuff when you have access to polarization information that you can observe. One of the coolest things that you can do if you wear your polarizing sunglasses a lot, you'll spot safety glass a mile away because you go, why is there all these crazy squares and colors in this glass and like these cells? You take off your glasses, oh, there's nothing there. The reason, of course, is that they stress the glass in a particular way so that when it shatters, it's less dangerous. Okay? And you can see that underlying stressed crystal structure when you have polarizing sunglasses on. Okay? So, they're worth the entertainment alone, the entertainment value alone to buy a good pair because you'll just see all sorts of crazy stuff. Okay, so I think that'll do it for polarization. And we are ready to continue with some other topics. The very first thing we need to address is what happens when light goes into a material. So we've been talking about light just going through empty space, but how does light interact with the material? So let's say we have a perfect vacuum here, and then we pass into some kind of material here. Let's find out what happens. So out here, the light is traveling at speed c. C is a special character reserved for the speed of light in a vacuum. We will say that it has a wavelength, lambda naught, a frequency of f naught. And of course, those three quantities are related, as I mentioned earlier. A equals f lambda. So now let's talk about what happens when light enters a material. Well, it probably won't surprise you to learn that light slows down, now that it has to contend with going through stuff instead of just getting to go through nothing at all. Okay? That's one of the weirdest things about light, is that light doesn't require a medium, right? It doesn't have any stuff that it has to go through. Sound is a different story, right? Sound that you're hearing right now is the oscillation of air molecules. If you didn't have the air molecules, there would be nothing to oscillate. Light is a weird exception because it's the oscillation of an electromagnetic field. But that doesn't mean that light can't go through something. And what happens is the same thing, is that when light enters a material, there are charges within that material, and those charges will oscillate, and that is essentially what passes forward the message. But there is a slight delay, because now you are picking up charges which do have mass, and so their ability to oscillate is not instantaneous. So light will slow down as you have to go through something. Okay? So we now are going to switch to a character v sub n, in fact. That'll be the speed of light in a material, and that will be less than c. You will slow down. So again, c is a special character used only for the speed of light in a vacuum, in nothing. But you can also travel through stuff, and then we switch back to our good old letter v sub n. I'll talk about what the n is for. How do we quantify this slowdown? We quantify this slowdown with just a divider. That's where the n comes from. So n is the divider of how much we have to divide the speed of light by in a vacuum to get the speed of light in a particular material. This n, this is called the index of refraction of your particular material. It is a unitless quantity because it's just dividing out one speed to get another. And the definition of the vacuum is, of course, that it's exactly 1, but n is greater than 1 for all actual materials. And of course, n being greater than 1, the greater it is, the more you slow down compared to a vacuum light speed. So let me just give you some typical values. Air, the n value is 1.00059, I believe. Let me just double check that. No, 29. Doesn't matter. It's barely bigger than 1. And that's not surprising because, as you probably know, the air at normal circumstance is mostly empty space with just an occasional atmospheric molecule to bump into. So it's no surprise that light does not really slow down very much through air or really any kind of gas, right? So this, for all intents and purposes, is equal to 1 for almost all of our calculations. So we will not make any distinction between light traveling through a vacuum and traveling through the air. It's not worth it. The difference is in the 4th decimal place. The only exception that we could potentially make is comparing an air to a perfect vacuum. Say, for instance, the space to our atmosphere. Then there will be a slight difference in the n value, right? Question?
So I'm just curious about like things like slowing down and then speeding up, like in space. If you're looking at like very distant objects,
Are you talking about like seeing a distant like star or something like that?
Yeah.
Well, that's mostly empty space, right? There's barely anything out there in space, so the signal does travel basically at sea the whole way, right? 3 times 10 to the 8th meters per second. The reason why you get a significant time delay, you're looking at stars that are as they might have been 1,000 years ago, is because even going that fast, if you have a vast distance to travel, you'll still take a long time. So it's not particularly that the light slows down. I mean, yes, it might hit interstellar gas or something on occasion, but that's not generally what we're talking about here. So we're talking about, just as an example, what if we go into water, okay? Light can pass into water. Water is far more dense. There's way more things to run into. And anytime you run into some charges, those charges basically, pass the message along. They basically swallow and then burp out the light, and they pass along the message. So here, N is significantly higher. So the light will slow down quite a bit compared to a vacuum. And so on and so forth. If you get into something like diamond, diamond is, as you probably know, quite a dense material. It's one of the densest naturally occurring materials that's also transparent to light, right? It's clear. So here, you're starting to get into a very high index of refraction. So that's just shy of 3, which remember, that means that the speed of light is 1/3 of its speed in a vacuum. Now, 1/3 of this is still pretty fast, but you can actually, in this day and age, they've been able to fabricate man-made materials where the indices of refraction are in the excess of 100,000, which means that they can slow down light so much that you can outrun it. So there's a whole field of research called slow light applications. Basically, you're slowing down light so much that it's going at a snail's pace, okay? But again, you have to manufacture some very esoteric materials for that to happen. So we know that light slows down. We now have the equation for how that happens. Now let's look at how that affects the other properties of the light. Well, anytime there's a slowdown on the highway, you get a traffic jam. So as you can probably guess, the wave is going to compress, because new crests are going to be arriving from the vacuum faster than the crest can now get away in the new material, right? So we expect a compression of wavelength. So the wavelength in this new material we expect to be less than the vacuum wavelength. So the wavelength will compress. Now, let's talk about frequency. So I'm going to station my eye in the sky. This is my physics eyeball, which sets the perspective. And I'm going to have that observer here measure the arrival of crests from the vacuum, as well as the departure of those crests into the new material. And they can count the frequency. Crest, 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 crest. Well, note that they are measuring both the frequency at which the crests arrive from the vacuum and depart into the new material. The frequency is the same. The frequency does not change in the new material. So if you were counting crests out here, you would get crest, crest, crest. If you were counting them over here, you would get crest, 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 same frequency. Now how can that be if the crests are so much closer together? Why don't you see them more often? Well, remember that the light also slowed down. So even though the wavelengths are closer together, they're also traveling slower. So the frequency is the same. So that's something that we can actually use, is the understanding of what properties change and what properties don't as you go from here to here. We found that the wave speed decreases. We found that the wavelength decreases, but the frequency is actually the same. So if you look at the equation V equals F lambda, it's the F that's fixed. You cannot change the frequency of a wave going into a different material. Well, that allows us to realize that v must be proportional to wavelength. Meaning that if you go slower, your wavelength has to compress, just like we already reasoned out anyway. Now this gives us the ability to realize that if they're directly proportional, whatever factor v is affected by, so will the wavelength. So we can now write down how does the wavelength change. It's also cut by n. So as light goes into a material, not only will its speed decrease, its wavelength will decrease as well. So that frequency is the same. This is true, by the way, not just for light waves, but for sound waves. For instance, when you pluck a guitar string,